Alright, what's up everybody? So this video I hope to lay some kind of theoretical foundations for some of the directions that we're going to be going on this channel. And you can see here we have two of my major influences, Mr. L.E.J. Brouwer, who founded what's known as the intuitionist school of thought in mathematics, in which we view math as taking place in the mind of the human being. And so we have a perspective that is centered on the human experience of thinking about mathematics. And we're going to be somewhat agnostic as to the metaphysical reality of numbers or other mathematical objects. Although it does seem obvious that math relates to the world, or perhaps models or explains the world in some ways, we're going to view math as primarily something which happens in the theater of the human mind. And then, of course, we have Professor Wildberger here and his awesome channel, Insights into Mathematics. And in particular, his video series called Math Foundations was a huge influence on what we're going to be talking about. So we start with counting. All right, so this is our first experience, both as young children, but also in early human history with numbers, is that we are counting, i.e. 1, 2, 3, 4, etc. And we're using this to count discrete objects. So we could count cattle, for example. We could count people, of course. We could count stars in the sky, or you could try at least. You could count eggs. You could count marbles. Perhaps points in a game, and so on. Okay, and once we've established the counting numbers, the basic operations, addition and multiplication, follow quite naturally. And we also get subtraction and division, but they're a little more complicated because they are only defined in certain situations for these kind of primitive kind of numbers. Okay, and the first real problems that we run into is once numbers get to a certain size, doing arithmetic with them becomes not just complicated, but it can become impossible at a certain point, I dare say. And in this sense, numbers should be properly viewed as a kind of a field or a landscape which goes beyond our view. Okay, so if you've ever seen a diagram like this is a sort of set theory view of the natural numbers, and you can see there's a dot 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 after the first couple numbers, and then there's a circle drawn around the whole thing, and that circle is meant to encompass all of the numbers up to infinity. Okay, and this is a perspective that we will reject on this channel, and it's perhaps very similar to a model that you may have seen in cosmology, which looks something like this. So here is the Big Bang, and then this is supposedly the universe at different ages, and these little circles here are indicating basically the end of space, which kind of leaves the question as to what this is outside of that, or what is the perspective of the viewer here. But nevertheless, we're also going to be rejecting this point of view. Okay, we can't count to the end of numbers, and we can't see to the end of space. All right, and there's a very strong correlation between these things. So the perspective that we are going to have instead is something like this. So we will think about numbers which get larger and larger as analogous to objects which are farther and farther away. All right, and our view of space is something like this. This is the view of space from an observer. Okay, and of course this is done with the Hubble telescope, and we can use a telescope to see much farther than the naked eye. In the same sense, we could use a calculator to do arithmetic with numbers which are much larger than we could do in our heads or with paper and pencil. But still there's a limit. And so again, you can see these two situations are analogous, and it's important from the perspective of what we're doing here on this channel that we have a more kind of humble, human-centered point of view where we can't draw a circle at the end of infinity or at the end of space. So once we've established the counting numbers, we get these laws of arithmetic. Okay, and hopefully these are somewhat intuitive. I hope you've seen these before, and this will kind of be our foundation. So rather than something abstract like ZFC, set theory, topology, something that you might think more advanced, this is going to be the main foundation of our mathematics, and we're going to try to build our arithmetic up from here. Okay. Oh, that was a mistake there. So the next extension of our numbers comes from when we are measuring rather than counting. Okay, and I want you to appreciate that there's a significant difference between these two applications of numbers. Okay, so now instead of counting objects, we're measuring some kind of quantity that is continuous, meaning it could be extended indefinitely, and it's divisible, which means it could be divided into smaller and smaller pieces indefinitely. Okay. Some examples, of course, would be distance, area, volume, time, weight. We might add temperature, pressure, and so on. So I should mention that numbers are not necessarily inherent to measuring. So we can measure certain things without using any numbers at all. We can, for example, take a rope or a piece of string or a stick that we make little notches on and measure a segment, and then perhaps for a construction project, and then or carpentry, we can take that rope to the piece of wood that we need to cut and see how long it needs to be, and so on. And we never had to introduce any numbers in the equation, and this is how many early people would have done certain primitive measurements. Okay, now when numbers come in is when we are comparing two distances or two measurements. It could also be area or weight or whatever. And so what we're really talking about now is proportions. So before we were using the natural numbers to count whole objects, now we're talking about a proportion. For example, we might have a segment here, a segment here, and let's say, I kind of eyeballed this, but let's say that these are in the proportion 3 to 4. Okay? And a very important tool for this is what's known as Euclid's algorithm, and you can see an example of this here. I won't go into detail, you can learn about it elsewhere, but the interesting thing is that we're actually using division over the natural numbers where we end up with a remainder. So here's a remainder here, and then we divide there, and that forms a remainder, and so on. And this allows us to find what's called a commensurate unit. And so Euclid's algorithm is often taught as a way of finding a greatest common factor between two numbers, or reducing a fraction to its simplest form. But it was actually originally developed as part of geometry. So let's say we have two segments here, and we want to find what is their commensurate unit. So we're looking for some smaller segment that we can count, or that we can break each one of these up into a whole number of parts of this. So let's say this one ends up being roughly, what is that, 8, and maybe this one is 7. Oops. Sorry, that's a little sloppy, but you get the idea. It would be in the proportion 7 to 8, and that's something that we could use Euclid's algorithm to find. Okay, so once we have established proportions, and then it's a step that I kind of neglected to mention but is worth mentioning, is once we have a standardized unit like an inch or a foot or a mile, then we can sort of move from proportions to fractions, which is a subtle but meaningful distinction that we'll perhaps cover another time. But once we have fractions, we can establish the 4 operations of arithmetic over the fractions. Okay, and of course Euclid's algorithm is also a part of this. So everything on this page basically encompasses how we could do arithmetic with fractions. Okay, now it should be mentioned that when we extend arithmetic to a new system of numbers, so we've gone from natural numbers, counting numbers, to fractions or proportions, you could say. These operations, even though we use the same symbols and we think about them as being roughly the same, there is a kind of a subtle difference. It's most obvious, for example, when you look at division. And when we do division over the natural numbers, we end up with a remainder. And when we do division with fractions, we're multiplying by the reciprocal. And that's actually quite a substantial difference that is important to understand. The last thing that I should say about this is that whenever we are moving to a new system of numbers or extending our arithmetic to a wider understanding of numbers, we have to redefine arithmetic and prove those basic laws of arithmetic with reference to the slide I showed earlier with the laws of arithmetic over the natural numbers. So this might seem tedious, but we skip these kind of steps at our own peril, and maybe we can assume that we know how to do arithmetic with something like irrational numbers or real numbers, which we'll cover another time. But unless it is explicitly laid out the way I have done on this slide, we can't assume that we know how to do arithmetic with a certain type of number. So this is an idea that will sort of further this connection between space and the continuum on the one hand and numbers and arithmetic on the other. So just like I was comparing the natural numbers, and as they get larger it's analogous to objects which are farther and farther away in space, when we're looking at fractions which have a larger and larger denominator, that's analogous to objects which are smaller and smaller and smaller and disappear in a similar way as objects that are very far away do. And a beautiful depiction of this is what's called Ford circles. So again, this is something that you could read more about if you're interested, but basically we have these circles which are all tangent to the circles next to them, and they're all tangent to this line on the bottom, and they touch that line at a point which we could think of as a point on the number line, and every fraction that you can think of in its simplest form is represented. So here we have the fraction 7/4. No matter how complicated, let's say 137 over 91. That's going to be, oh, I can't say exactly off the top of my head, but maybe somewhere in here, right? And you can see that it's almost like this froth of bubbles, but as the denominator gets bigger, the fraction kind of takes on more complexity. So something like 1/2, which is quite easy to understand and to do arithmetic with, is kind of visible at this sort of base level, whereas a fraction like I was saying with 91 in the denominator, that will take some zooming in and to really see. And so in the same way that natural numbers getting larger encompasses this problem of space extending beyond our view, rational numbers getting more and more complicated with a larger denominator is analogous to the problem of understanding space as we zoom in microscopically. So we have this telescopic aspect of large natural numbers and this microscopic aspect of more and more complicated fractions. So just to wrap it all up, this kind of sets us up for this fundamental distinction in mathematics. One of the most important distinctions in mathematics is between the discrete and the continuous. So on the one hand we have counting, on the other measuring, which we covered. Counting is of course modeled by the natural numbers, measuring by fractions, and then eventually the rational numbers. Eventually discrete mathematics is going to lead us to the study of number sequences, whereas the continuous mathematics leads us to the study of curves. And here's sort of a picture of a discrete graph and a graph of a continuous curve. So we're going to wrap up this video here. There's going to be more. Next time I hope to go into another key distinction, which is between the exact and the approximate. But I hope this has helped you to maybe think about some of these foundational ideas in a different way, and I'm really excited for where we're going to go to explore and look at some of these old questions with perhaps some new eyes. So thanks for listening, and I will talk to y'all later.